In this video, we're going to explore using a titration and its plot to solve for an unknown chemical. So in this case, imagine a situation where they're clearing out an old building and there's some unidentified bottles down in the laundry room. Well, hazmat's got to figure out what they are, and so they can, depending on what they think it might be, do a few experiments to determine what it is. Now, if you got a full research lab with a mass spectrometer or a nuclear magnetic resonance device, an NMR you can use, you can actually figure out exactly what's in your solutions. Pretty straightforward. However, those machines aren't always available. They're not necessarily easy to access, and a lot of times it's just cheaper to add some sodium hydroxide to it, or some acid. Today, that's what we're going to do. The solution was tested early on, and it was found that it was fairly basic, and so we're going to add 0.75 molar hydrochloric acid. And indeed, that was done. Solutions were added, pH was monitored as it reacted, and this curve was observed. Using this info and some likely common household chemicals, we're going to determine what we think the solution was and what its concentration was. Go ahead and give us a try. See if you can pull some information out of this plot and determine what you think this species was and its concentration. Then unpause and come on back. All right, if you're back, well, what do we see when we look at this plot? What I see first is it's kind of curving down over here. And then it's speeding up its curve over here, and then it's slowing down its curve over here. This plot definitely has some curves, and it's got more than one inflection point. Well, if this was a strong acid and a strong base, we would expect that we would just have the one inflection point and should be based around pH 7. Well, the one that's extreme change tends to be when you go through the equivalents, when you wipe out any of the other chemical, and well, in this case, there's just HCl left. So this later region would be dominated by the HCl. And that makes sense. We're pretty low pH at that point. So 0.75 molar HCl being added and all the other species have been consumed, we should be pretty low in pH. That means this change here must be when we're reaching the equivalents, when whatever our basic species is has just been matched by the strong acid we're adding. So that would be somewhere around the middle here. That's 3 to 4-ish. Let's say it starts up about 6 and it levels off about a little under 2. So 3.5, 3.7, 5-ish, somewhere around right here. Well, that's not 7. So this is not a strong base, which we kind of had a hint on when we had an extra inflection point happening earlier. But checking our equivalence point definitely helps us know that that was not a strong base we were starting with. Well, what could the species be, though? Well, it was basic to begin with, and while I gave us the pKa's for several forms of acid, we can have the deprotonated versions of all of these, and we can solve what the pH for those would be. You definitely have an ammonia solution, or a hypochlorite solution, or a formate solution, an acetate. There's a lot of reasons we could deprotonate these too. If that's the case, where's our inflection point? It's going to be somewhere in the middle here. Well, if this is our kind of equivalence point, about what, 44 milliliters? So 22-ish should be halfway to the equivalence. So right here, assuming we started all something basic, as we added some H plus and we added some H plus and we added some H plus, we're getting a little bit of mix. We're getting a little less B minus and we're getting a little bit of HB. We're getting a little bit less B minus, a little bit more HB. And right here, they should be equal. If 44 milliliters is what it took to get rid of all of the base, then half that volume should have gotten rid of half the base. Well, we're putting protons on it with a strong acid, so how do we get rid of B minus? We create HB. We create the conjugate acid. Well, if I'm at equal amounts, then whatever pH is right here, this should be my pKa. Remember that our pKa is equal to the pH in a 50-50 mixture, our weak acid and our weak base. Well, that's going to be about 7.5-ish. So we go look, and probably not hydrogen peroxide, probably not acetic acid, probably not formic acid. Well, hey, it does seem to match up pretty well for hypochlorous acid. So this could be a mixture of hypochlorous acid. It's not for certain, but of the likely household chemicals that would probably be in this laundry room, it does match up pretty nicely. What is hypochlorous acid? Most commonly we know it as bleach. Sodium hypochlorite is bleach. Usually around 3 to 5% is the home bleach you can buy. So if we have a reasonable idea based on the inflection points and where we think the pKa for that species was based on the equivalence point we see at the end, well then let's use that volume to go about solving the concentration. If this is indeed bleach, what would our concentration be? Well, we added 44 milliliters, approximately, of HCl in order to reach the equivalence point. So 0.044 liters of the HCl solution. And we have the concentration of it. In every 1 liter of my HCl solution, there was 0.75 mole of HCl. So I can figure out just how much HCl we actually added to react all of our starting material. We added 0.033 mole of HCl. Well, we're protonating to make HClO from ClO minus, and so it's 1:1, and so that must translate into 0.033 mole of the ClO minus, which if it was bleach, translates into 0.033 mole of sodium hypochlorite. That is, it gives us the moles of our hypochlorite, and so we can calculate out the molarity. Well, we used 50.00 milliliters of the unknown when we started. And so I have the volume of the solution and the moles of the unknown that must have been in that volume. So 0.033 mole of the hypochlorite over 0.050 liters of the unknown solution, giving us a 0.66 molar hypochlorite. Well, if indeed that did come from sodium hypochlorite, I can say in 1 liter, I must have 0.66 mole of NaClO, which I can translate into mass. Let's see if it matches the kind of 5% standard home solutions. So if you've solved molarity, really that was probably the concentration most folks would have solved when we asked you to pause earlier. But let's compare to what we'd find on the bottles. And so indeed, hey, in 1 mole of NaClO, there's so many grams of NaClO, 74.44, which means there must have been 49.13 grams of NaClO in that 1 liter. That would have been the weights of sodium hypochlorite we would have needed to make a 0.66 molar solution. And if we think about weight percents, well, it's grams over 100 milliliters, and presently we have 49.13 grams over 1,000 milliliters. So really it's just shifting a decimal, 4.917 grams of sodium hypochlorite, which, yeah, approximately 5%. So just by doing a titration of a sample of our unknown solution, taking the plot and using it to find various pieces of info. Hey, how much was the total amount of HCl required to react with all of the basic starting material? Half that gave us, well, I must have half weak acid, weak base, which lets us identify the pKa so that we could figure out which species we were probably looking at from our likely list. We then could use that concentration of HCl and the total volume that required to figure out just how much of the base species was actually in our solution. Since our equivalence point at the end is when our HCl equals our basic species that we started with, we can use that to solve the amount of the basic species we began with. We found that it was 0.66 molar. And then if we wanted to translate that into what's commonly labeled on household bottles, we find that it was equal to roughly 5% weight to volume sodium hypochlorite. So this matches up pretty well. Probably that unknown bottle was indeed a bottle of bleach, which might explain why the label was gone. If they'd spilled it on the label, it could have destroyed all the pigments and wiped out the label quite a while back. Titration plots are actually very useful for pulling information about an unknown chemical out. Where the inflection points are and what volumes it took to react tell us a great deal about what the species is and how concentrated that species was.